So, am I audible, Jumena?
Yes, sir, you are.
So, what was the last topic that we were doing? The last topic that we did on Saturday. We have completed up to potential energy, right?
Yes, sir. We did few questions even.
Few questions. The last numerical was?
Potential energy, no, it's like calculate potential energy of the system,
Okay.
which having 2 points
Okay.
and 2 charges.
Right. So it was basically electric. We did the last topic was potential energy of 2-point charges in electric field, right?
External field, in external field.
The next is potential energy of dipole. Potential energy of electric dipole in uniform electric field. Potential energy of electric dipole in uniform electric field. So this is a uniform field. So in this uniform field, Fatima, I just have started this topic, potential energy of electric dipole uniform electric field. So in uniform field, I placed a dipole. Let's say this is the dipole. Fatima, what do you mean by dipole? What is electric dipole?
When two charges are equal and opposite.
I'm having two equal and opposite charges, right? So this is the dipole moment. I'm not showing charges, that's the dipole moment. And this dipole is placed at an angle theta. So Juvena, what will happen with this dipole? If you place the dipole at an angle theta with the field, what will happen with the dipole? Will it remain at rest or it will experience something?
It will experience.
What? It will experience what?
It will experience force.
Right. Not force.
Flux.
Torque. Electric field will exert a torque on the dipole. Electric field will simply exert a torque on the dipole. And that torque is given by this expression. Torque is the cross product of P and E. This is the expression of torque. The torque experienced by dipole is P cross E, it's P cross E. Angle between P and E is theta. So that is PE sine theta. That's first equation. So the torque experienced by dipole is PE sine theta. That is the expression of torque. This torque will try to rotate this dipole along the clockwise direction. But I want to rotate this dipole in a direction which is exactly opposite to that of field. I just want to rotate this dipole in a direction opposite to that of field. So initially, let's say dipole was at this angle. Now I would rotate it like this. So this is the direction of dipole moment. This is the direction of electric field. This angle is theta. So we are rotating this dipole from angle theta 1 to angle theta 2. We are rotating this dipole in anti-clockwise direction. So when the dipole is at angle θ1 with respect to field, it will interact with field, and due to that interaction, this dipole will have some potential energy U. When this dipole is at angle θ2 with the field, it will again interact with the field and it will have some potential energy U. We have already did in the first class of potential energy that whenever two charges interact with each other, due to interaction, that particular charge will have some potential energy. Here, instead of a charge, we have dipole. Your dipole will interact with field, and due to that interaction, the potential energy is U1 when dipole is at angle θ1. When dipole is placed at an angle θ2 with the field, the potential energy is U2. You're supposed to calculate this change in potential energy. To calculate this change in potential energy, that is U2 minus U1, you need to calculate work done in rotating dipole from θ1 to θ2. Okay, now tell me. This torque is acting in clockwise direction. This torque is acting in clockwise direction. So can this torque rotate dipole in anti-clockwise, or you need some external torque? Can this torque due to electric field rotate dipole in anti-clockwise direction, or you need some external torque?
We need some external torque.
You need some external torque. So external torque to be applied. So you need to apply an external torque. So an external torque to be applied, tau external, is exactly minus of torque due to electric field. Both the torque would be in opposite directions, but their magnitudes are same. So tau external is minus of tau. That is equation number 1. Or I can even open this cross product. So Jubaina, if I open this cross product, what would be the final result? If I open P cross E, the final result? Fatma, if I open this cross product P cross E, what would be the final result? No answer, huh? PE, good. PE sine theta. So that's my first equation. And this torque is acting in clockwise direction. This torque is acting in clockwise direction. Now we need to apply an external force on the dipole to rotate it from angle θ1 to θ2. That external torque is in a direction which is exactly opposite to that of θ. So tau external is minus of tau. Just note it down up to this point. Afroza, am I audible? Afroza. Am I audible, Afroza? Okay. So see, I'm just revising it. The first topic is potential energy of electric dipole. Okay, I'm coming to it, Fatma. Potential energy of electric dipole in uniform electric field. So if we took any uniform electric field, in this uniform field, we just placed a dipole P. The electric field will exert a torque on the dipole, and the torque is given by P cross E. Or if you open this cross product, it's PE sine theta in the clockwise sense. This torque will try to rotate the dipole and will finally try to align it in the direction of field. We want to calculate the potential energy of dipole. For potential energy, we need work done against the electric field. But now we want to calculate potential energy in two positions. To calculate potential energy, we have to rotate it from one position to another. For to calculate potential energy, we have to carry system from one position to another. So when the dipole is at position θ1, its potential energy is U1. When your dipole is at position θ2, its potential energy is U2. To calculate this potential energy, you need to rotate the dipole. That's why we are rotating dipole. But this rotation should be against the electric field. Now, since electric field is rotating this dipole in the clockwise sense, to calculate potential energy, you need to rotate this dipole against the field, means in anti-clockwise. That's why we are applying this external torque. And that external torque is negative of torque due to electric field. Afroza and Fatma, your doubt is clear? Just to calculate potential energy. We are rotating just to calculate potential energy. Okay. So if I calculate the magnitude of external torque, then magnitude of external torque is equal to magnitude of torque due to field. That's equation. We can substitute 1 in 2. If we substitute 1 in 2, then tau external will comes out to be Pe sine theta. P sine theta, that is equation. So this is the external torque acting on the dipole, which is Pe sine theta. Now you need to calculate work done by external torque, to rotate dipole from inclination theta 1 to inclination theta 2. So that work done by external torque, the formula of work done is its integral of tau external d theta from theta 1 to theta 2. This expression is of class 11. This was in class 11 syllabus. That if you are calculating work done by force, then that work done is F dot dx integral. If your work done is by torque, then that is torque into angle from theta 1 to theta 2. That is equation number 4. So I'm using this expression from class 11 syllabus. That work done is torque into angular displacement. Now, if I substitute 3 and 4, then you will get that work done by external torque will be its integral from theta 1 to theta 2, tau external is Pe sine theta t theta. So work done by external torque is, you can take this Pe outside this integral sign. This is only theta 1 to theta 2. Afroza, what is integral of sine theta? We have discussed integration of sine theta earlier. Okay, so open question for all. Afroza, Fatma, Jubaina, what is integral of sine theta? Okay, no one remember, huh? Yes, not cos theta, Fatma, this is minus of cos theta. Integral of sine theta is minus of cos theta, limit is from theta 1 to theta 2. Okay, note it down up to this point, then we will substitute the limits. No, Jubaina. Integral of cos theta is sine theta. The differentiation of cos theta is minus sine theta. So this negative sign is of reverse order in differentiation and integration. If you differentiate sine theta, you will get cos theta, but integration of sine theta is minus cos theta. So shall I erase it? Okay. Padma, I'm erasing it. Huh? Okay, if I solve this integral, then work done is minus of PE, its integral of cos theta, limit is from theta 1 to theta 2. So this is the work done by external torque. Work done by external torque is, it's minus of PE, it's cos theta 2 minus cos theta 1. So this is the expression of work done by external torque. And this work done by external torque is exactly equal to potential energy difference. This work done by external torque is equal to potential energy difference. This is how we calculate potential energy. Potential energy difference. So potential energy difference delta U is equal to final potential energy minus initial. It's U2 minus U, which is equal to work done by external torque, which is, so your potential energy difference delta U is minus of PE cos theta 2 minus cos theta 1. This is how we calculate potential energy. And this is the expression of work done by external torque. Work done by external torque is minus of PE cos theta 2 minus cos theta 1. But if I want to calculate work done by electric field, work done by electric field, we want to calculate work done by electric field now. So here, work done by electric field is exactly negative of work done by external torque. Work done by electric field is exactly negative of work done by external torque. The reason is the torque due to electric field is clockwise, but the torque due to external torque is acting in anti-clockwise direction. So both the torques are acting in opposite direction, so their work done will differ by a negative sign. So you can say that your work done by electric field is negative of this thing. It's minus of PE cos theta 2 minus cos theta 1. So work done by electric field is, it's PE, it's cos of theta 2 minus cos theta 1. So this is how we calculate work done by electric field. Am I audible, Johanna?
Yes, sir.
Okay. So we're doing chapter number 2 here. So work done by electric field is just negative of this. So that's PE cos theta 2 minus cos theta. Now, after one work done by electric field, he can ask you to calculate potential energy. He can ask you to calculate just potential energy. So, Jubena, this is potential energy or potential energy difference?
Potential energy difference.
Potential energy difference. Let's name these equations. Let's say this is equation number 1, this is equation number 2, and this is equation number 3. In equation number 2, we have calculated potential energy difference. But instead of potential energy difference, if I ask you to calculate potential energy, means you need not calculate the difference between two potential energies. You need potential energy at a particular angle. So to calculate potential energy, we can use equation number 2. Using equation 2. So using equation 2, potential energy difference is, it's minus of PE, it's cos theta 2 minus cos theta 1. See, delta U means it's U2 minus U1. It's U2 minus U1. If I multiply with this minus PE here, let's keep this negative sign inside. This is PE cos theta 2 minus PE sin theta 1. Oh, sorry, not sin. PE cos theta 1. Okay, can you guess the contribution U1? Okay, which one is U1 out of these two terms and which one is U2? Fatma, can you guess which one is U1 out of these two terms and which one is U2?
U2 is PE cos theta 2 and U is P
Sin theta, cos theta 1. Okay, Afroza, can you guess the value of theta 1 for which U1 is 0? I need just U2. So let's choose a value of theta 1 for which U1 is 0. Afroza, can you decide a value of theta 1 for which U1 is 0? 90, very good. If I consider theta 1 to be 90 degree, that means initially your dipole is perpendicular to field. Then your U1 comes out to be 0 because cos 90 is 0. Theta 2 could be any angle, and we can write U2 as U now, because if U1 is 0, there is no point in writing U2. If I make these substitutions here, you will get U minus 0 is minus of PE cos theta minus PE cos 90. Cos 90 is 0. So your potential energy is simply minus PE cos theta. This is how we calculate potential energy. At minus of PE cos theta. So there is difference between these two relations, relation number 2 and relation number 4. In relation number 2, you are calculating difference in potential energy in two orientations. The first orientation is when your dipole is at an angle theta 1 with the field. The second orientation is when your dipole is at an angle theta 2 with the field. But here, this is equation number 4. There is just one orientation, means if your dipole is placed at an angle theta with respect to field, then your potential energy is minus of PE cos theta. So for the point of view of numericals, these four expressions are important. The first one is work done by external torque. The second is potential energy difference. Then third, work done by electric field. This is work done by electric field. And also the potential energy, not the difference, just the potential energy. Just note it down. And tell me if you have any doubt. Johanna, if you stuck somewhere, just feel free to ask. Afroza, either you can get derivation, it's a very important derivation, or you can also get numericals on this concept. We will do some special cases. One marker and objective questions can be made from those special cases. Or is an important derivation?
So why are we substituting the value? I mean, why are we changing the value 90 and now substituting it? I mean, why are we making it zero?
Because we, in this expression, what we have is U2 minus U1. We have difference in potential energy. But we don't want U2 minus V1. We want to calculate U. So the simplest thing is choose an orientation in which U1 is 0. Because if U1 is 0, then you can easily calculate U2. There is no other way in theoretical physics to calculate absolute potential energy. We always calculate change in potential energy, and then using that change, we choose the initial position or orientation in this case because it's an angle. We choose initial orientation in a way that potential energy in the initial orientation reduced to be 0. Mathematically, we can always calculate difference in potential energy. But to calculate potential energy, absolute potential energy at one orientation, you need to substitute this initial position, or you have to choose this initial position in a way that initial position potential energy comes out to be 0. If it comes out to be 0, then you can easily calculate your U, which is minus of P cos 0. I substitute it to be 0 just to calculate this value U. Otherwise, that work done will always give difference in potential. That's the only method. Yes, Afroza, I will give you. I will show you. Okay, so shall I erase it? Fatma, is it clear? Your doubt is clear? Why we are taking U1 to be 0? So, can I erase it? The next is, then there are some special cases like case 1. Case 1 says if dipole moment is parallel to field. If dipole moment is parallel to electric field. If your dipole moment is parallel to electric field. So this is electric field. And your dipole is placed just parallel to field. Can you guess angle between electric field and dipole moment? What is the angle between? Yes, P and E are parallel. That means angle between them is 0 degree. So if I calculate potential energy, this comes out to be minus of PE cos 0. Cos 0 is 1. So potential energy is minus of P. Your potential energy is minimum. So if your dipole is parallel to field, then your potential energy is minimum. This is minus of PE. The minimum value of minus of PE cos theta is minus P. Because it's negative, so it would be negative, it will be minimum if your cos theta is maximum. So the maximum value of cos theta is 1. So we can say that this minus of PE is the minimum value of minus of PE cos theta. And when your potential energy is minimum, your equilibrium is stable equilibrium. We have already discussed equilibrium 2 times in chapter number 1. One when we were doing equilibrium, and second when we were doing torque on a dipole in uniform field. So earlier we decided stable or unstable equilibrium by just disturbing your system. Now we are deciding stable or unstable equilibrium just by looking potential energy. If potential energy is negative, or if your potential energy is minimum, then your system is in stable equilibrium. If potential energy comes out to be maximum, like in case 2, if I say that if dipole moment is anti-parallel to field, is it clear? The first part, case 1, the case when the P and E are parallel. Let's start with case 2. If dipole moment is anti-parallel to field, dipole moment is anti-parallel to field. Anti-parallel means they're acting in opposite directions. This is your electric field. A dipole moment is acting in exactly opposite direction. This is the direction of dipole moment. So if they're acting in opposite directions, that means angle between them is 180 degrees. So if we calculate potential energy, it comes out to be minus of PE cos 180. Cos 180 is minus 1. So potential energy is minus of PE cos 180 is minus 1. So potential energy comes out to be plus P. So you can say that your potential energy is maximum. And when your potential energy is maximum, this is case of unstable equilibrium. Then it's case 3. If your dipole is perpendicular to field, case 3, if dipole moment is perpendicular to field. If your dipole moment is perpendicular to field, means if this is electric field and this is your dipole moment T, angle between them is 90 degrees. So theta is 90 degree here. If we calculate potential energy, it's minus of PE cos 90. So potential energy is 0. It's neither minimum nor maximum. It's in between minimum and maximum. So if your potential energy is neither minimum nor maximum, that means your system is not in equilibrium. This is not the case of equilibrium. So there is no point in deciding stable and unstable equilibrium for this case. Stable and unstable are type of equilibrium, but in case 3, there is no equilibrium. So you won't write this as stable or unstable here. Just note it down. And tell me if you have any doubt in it. Johanna, are you getting it? So can I erase it? Okay. So that was about potential energy of dipole in a uniform field. So first thing is you need to calculate work done by external torque, then work done by electric field, then potential energy difference, then potential energy, and then these cases of equilibrium. Solve one numerical based on this concept. An electric dipole of movement 2 coulomb meter is placed in uniform electric field of 5 Newton per coulomb. Uniform field of 5 Newton per coulomb. Calculate first part. Work done by external torque to rotate dipole from position of stable equilibrium to unstable equilibrium. So from position of stable equilibrium means your initial angle is 0 degree. To unstable equilibrium means your final angle is 180. Second, hence calculate potential energy difference. Third, also calculate work done by electric field. Fourth, potential energy if dipole is placed at 60 degree with respect to field. You have to calculate potential energy if your dipole is placed at 60 degree with respect to field. Solve it and report your answer in chat room. You can directly calculate answer of part 2 and part 3 from part 1. First calculate part 1. Using part 1, you can easily calculate 2 and 3. Answers. Padma, you can substitute the values of theta. Na? Theta 1 is 0, theta 2 is 180 degree. Cos 180 is -1. So you'll get a number. Okay. Okay, Afroza. No, Fatma, it won't be 0. See. Okay, I'm solving it now. Johanna, your answers? So in the first part, you're supposed to calculate work done by external torque. So work done by external torque is simply minus of PE, it's cos of theta 2 minus cos theta 1. Next, we can substitute the values. P is 2. Okay, good. E is 5. It's cos theta 2. Theta 2 is 180. Theta 1 is 0. So work done by external torque is, it's minus 10. Cos 180 is minus 1. Cos 0 is minus 1. So work done by external torque comes out to be 20 joules. It's not 10, it's 20 joules. Jubaina was getting the right result. It's 2P, right? It's 20 joules. That's first part of the question. Clear? Fatima, Afroza, Johanna. Is it clear? This 20 joule? Sure. Okay. Second. The next is potential energy difference. So here, potential energy difference is exactly equal to work done by external force. You can simply write that potential energy difference is equal to work done by external torque. So you can write potential energy difference is 20. That's it. Third one. The next is you need work done by electric field. Johanna, is it clear? Work done by electric field is just negative of work done by external torque. So work done by electric field here is minus of 20. That's third part of the question. Part 4. The last part is you need potential energy if dipole is placed at 60 degree with respect to. So if dipole is placed at 60 degree, then potential energy is minus of PE cos 60. So potential energy is minus of PP is 2, E is 5, cos 60 is half, gets cancelled out. So potential energy is minus of 5. Okay, any doubt in these four parts? Doubts? Afroza, Johanna, is it clear? No, Afroza, it's 2 coulomb meter. It's 2 coulomb meter. It's SI unit. This is an SI unit, not the CGS one. The SI unit of dipole moment is coulomb meter. So this is okay. No, it's not millicoulomb. It's coulomb meter. So can I erase it? Okay. Okay, so I'm erasing it. So that was about potential energy of dipole in uniform electric field. Okay, after potential energy of dipole, the next is electrostatics of conductor. The next topic is electrostatics of conductor. That's the second part of chapter number 2 is divided into 3 parts basically. The first one is potential and potential energy. The second is electrostatics of conductor and dielectric, and the third one is capacitance. So that's basically the second part, electrostatics of conductor. Let's start with conductor. So what are conductors? Conductors are materials which can conduct electricity. Conductors have free electrons. All properties of conductors are due to free electrons. If you have conductor have positively charged ions. They have positively charged ions and free electrons. All properties of conductors are due to free electrons only. So conductors have free electrons which are responsible for electric conductivity. So all properties of conductors are due to these free electrons only. These electrons are absolutely free to move within the body of conductor. These electrons are free to move within the body of conductor, are free to move within the body of conductor. So these electrons are absolutely free to move within the body of conductor. They can move freely throughout the body of conductor. And all properties of conductors are due to these free electrons only. So let's start with some properties of conductor. Properties of conductor. Okay, first property. Jubena, what should be the net charge inside a conductor? A conductor is negatively charged, positively charged, or is it neutral? Jubena?
So it's neutral.
Neutral. It have equal amount of negative and positive charge. So net charge inside a conductor is 0. Now, if I charge a conductor, I take a conductor and provide charge over this conductor. I am providing some extra charge over the conductor. Then this charge will always resides only on the outer surface. If you try charging this conductor, then charge will reside only over the outer surface of conductor. There won't be any charge inside the conductor. Even if you charge a conductor, then charge will reside only on the outer surface. Even now, the net charge inside the conductor is 0. This is property of conductor. Whenever you try charging a conductor, that charge will reside only on the outer surface. Inside the conductor, net charge is always 0. Charge resides only on the outer surface of conductor. So charge will reside only on the outer surface. There is no charge inside the conductor. The net charge inside a conductor is 0. Just note it down, then we'll do some more properties of conductor. Both the next topic, capacitance, as well as chapter number 3 are based on conductors. We will use these properties of conductors even in chapter number 3 in current electricity. Okay, can I raise it? Jubena, Juhena. So that's the second property of conductor, that net charge inside a conductor is zero. Even if you charge a conductor, that charge will reside only on the solid surface. There is no charge inside the conductor. Third property. Electric field inside a conductor is zero. Electric field inside a conductor is zero. Is zero. If you have a conductor, charge will always resides on the outer surface. Inside the conductor, charge is zero. If charge is zero, then it can be proved that electric field is zero. We can prove it using Gauss law. If I consider Gauss law, using Gauss law, let's consider a closed surface. Then Gauss law says closed integral of E dot ds is Q enclosed by epsilon naught. So if your Gaussian surface is within the conductor, then inside that Gaussian surface, the net charge is zero because Q enclosed is always zero. Q enclosed is zero. If your Q enclosed is zero, that means closed integral of E dot ds is zero, which simply means that electric field inside the conductor is zero. So the simple two-line proof that if charge inside a conductor is zero, then according to Gauss law, electric field is always also zero. Is it clear? This third property, this proof of third property. Okay. Next, fourth one. So electric field inside a conductor is zero. The next is electric field is perpendicular. Electric field is perpendicular to surface of conductor perpendicular to the surface of conductor, and its value is sigma by epsilon. So electric field is always perpendicular to the surface of conductor, and its value is sigma by epsilon. So if I consider a conductor of any arbitrary shape, say positive charge is distributed over the conductor, then the electric field is always perpendicular to the surface. Then it's sigma by 2 epsilon. Sorry, sigma by epsilon. N cap. N cap simply shows it's perpendicular. N cap is a unit vector which is perpendicular surface. What if it has more than one surface? Fatma, it doesn't matter the number of surface this conductor has. You can have a conductor in this way, right? This have multiple surfaces. Electric field on each surface would be perpendicular to it. If it is conductor, then electric field is always perpendicular to the surface of conductor. That's it. It's absolutely independent of the number of surfaces. By the way, what is sigma here? Afroza, what is sigma? What sigma represents? What sigma represents here? Afroza. Okay, no response means don't know. Jabana, what does sigma represents here?
Is it surface charge?
Yes, this is surface charge density. Means charge per unit area. Okay, just note it down, then we will prove it. We will prove this property. It's an important property, this last one. Surface charge density, sigma. Okay, just note it down, then we will prove it. Can I raise it? Jabana, Johanna. Okay. Next, proof of this property. We will prove this property using Gauss law only. So let's consider a conductor of some arbitrary shape. The charge is distributed only on the outer surface. So the surface charge density of this conductor is plus sigma. The charge here is distributed only on the outer surface. So the surface charge density is plus sigma. To calculate electric and electric field, as we have discussed, it's perpendicular to the surface of conductor. It's always perpendicular to the surface of conductor. To calculate this field, let's consider a cylindrical Gaussian surface. Consider a cylindrical Gaussian surface. The area of the end is delta S. I have placed the cylinder in a way that the top surface of the cylinder coincides with the surface of the conductor. The rest of the cylinder is inside the conductor. Only the top surface coincides with the surface of conductor. The rest of the conductor, the entire conductor is within the conductor. Entire this cylinder is within the conductor. Johanna, can you just tell me what is the value of electric field here? At this point of cylinder, the value of electric field? Johanna. Zero. Very good. Because this point is inside the conductor. So inside the conductor, your field should be zero. So let's consider. So let's consider a Gaussian surface having area of ends delta S. So let's consider a Gaussian surface. The area of the ends is delta S. First of all, let's calculate flux to the top surface. Let's calculate flux through the top surface. The direction of the top surface is perpendicular to the surface. That's area vector. This we did in chapter number 1 in Gauss law. That direction of area vector is always perpendicular to the area. So this area vector and electric field are acting in same direction. So flux through top surface, let's call this flux as delta phi. This flux is E dot delta S. Afroza, what is the angle between E and delta S here? Afroza. S is area, Fatma. S is area. Delta S means small area. That's the area of it. So Afroza, what is the angle between E and delta S? Okay. Fatma, what is the angle between E and delta S? The angle between E and delta S. What's the value of angle between them? It's not 180. No, it's not 90. See, electric field is perpendicular to the surface. Area vector is again perpendicular to the surface. They're acting in same directions. E and delta S are acting in same direction. Yes, that means angle is 0 degree. They're acting in same direction. Na? So this is E delta S cos 0. Cos 0 is 1. So your delta phi is E delta S now. That's first condition. This is flux to the top surface. Is it clear? This is equation number 1. Jabana. Okay. Next, I need flux through rest of cylinder. So Fatma, what is flux through rest of cylinder? This is through the top surface only. Fatma, what should be the value of flux through rest of cylinder? Okay, no response from Fatima. Afroza, will you try? What's the value of flux through rest of cylinder? No, Fatima. Afroza, what is the flux through the rest of the cylinder? The top surface of the cylinder coincides with the surface of conductor. The rest of the cylinder is inside the conductor. Okay, Jabana, will you try?
0.
0. Because else then this top surface, the entire surface of the cylinder is inside the conductor. Inside the conductor, your field is 0. There is no field. If there is no field, then flux would be 0. Is it clear, Fatma? Afroza? Let's call this as delta phi 1. Fatma, Afroza, is it clear? The rest of the cylinder is inside the conductor. Inside the conductor is no field. No field means no flux. Delta phi 2 is 0. Next, we can calculate the total flux. Total flux delta phi is sum of flux due to the top surface and the rest of the cylinder. Delta phi 2 is 0. So you can say that your delta phi is delta phi 1, which is E delta S. That's equation number 3. That's the total flux. We can even calculate this flux using Gauss law. Using Gauss law. Now we will use Gauss law. We will use Gauss law for the complete cylinder. So Gauss law says delta phi is delta Q enclosed divided by epsilon naught. Delta Q enclosed divided by epsilon naught. That is equation number 4. Here delta Q enclosed means this is delta Q enclosed. The charge enclosed in this much portion of the cylinder. Charge is distributed over the conductor. The cylinder is intercepting a part of the conductor. So there must be some charge which is enclosed by the cylinder. So you can say that delta Q enclosed is charge on area delta S of conductor. This cylinder is cutting an area delta S part of the conductor. So whatever the charge is on that area delta S, that charge is delta Q enclosed. Is this statement clear? This may be confusing for someone. Is it clear that delta Q enclosed is charge on area delta S of conductor? This last statement.
So can you explain one more time?
See here, the charge, the entire charge is distributed over the conductor. This is the charge distributed over the conductor. I take a cylinder which enclose a small portion of the conductor. The portion of the conductor which is inside the cylinder is equal to the area of ends delta S. Say consider this as the conductor. This my hand is conductor. This is the conductor. I'm taking a cylinder. I'm passing this cylinder through this conductor. So this cylinder will cut the area of my hand equal to the area of the ends of cylinder. If I'm passing the cylinder through this conductor, my hand, then this cylinder will cut a portion of my hand, which is equal to the area of ends of the cylinder, right? I'm using the same analogy. So the area of ends of the cylinder here is delta S. So this cylinder is cutting a portion of delta S here. It's cutting a portion of delta S of conductor here. So whatever the charge over the area delta S of conductor, the same charge is enclosed by the conductor. Johanna, Afroza, is it clear now? Johanna, if it's not clear, be very frank, I can repeat it again. There's no issue. Johanna, you got it? That this delta Q encloses charge on area delta S of conductor. Next, you can write your sigma as, your sigma is the ratio of charge and area. So you can write this as delta Q enclosed divided by area, which is delta S. You can write your delta Q enclosed as sigma into delta S. That's equation number 5. We can substitute the value of delta Q enclosed from 5 and 4. If I substitute 5 and 4, then we'll get that delta phi is sigma delta S over epsilon. That's equation number 5. Now we can easily equate 3 and 5. Equating 3 and 5. Now if we equate 3 and 5, we will get E delta S is sigma delta S by epsilon. Okay, I don't have much space now. Just note it down and get the value. This delta S gets cancelled out from both the sides and you'll get that your E sigma by epsilon. Just tell me if you have any doubt in this calculation. It's an important calculation given in NCERT. You can't skip it.
Sir,
Yes.
after substituting 5 and 4, the next equation, right? It's 6, right? Equation number 6.
Yes, it's 3 and 6. What is the syllabus of your midterm? Your midterms are in Sept end or in October first week, right? What is the syllabus of your midterm? You have a recent exam, na, in October first week?
They informed us.
They haven't informed you. It's okay. So when you equate them, you get your E is sigma by epsilon naught only. So this is electric field on the surface of conductor. If you remember, we have done this calculation before in Gauss law. We have calculated for a sphere, a solid sphere having some charge Q. Because we get the same result on the surface of the solid sphere. And this result is absolutely independent of shape and size of the surface. See, if you have, this is electric field, but instead of a positively charged conductor, if you have a negatively charged conductor, say you have a conductor Here, charge distributed is positive, and here the distributed charge is negative. At this point, the direction of field is away from the charge. This is the direction of field. Over this point, the direction of field is towards the charge. This is the direction. Field is always perpendicular. But for the positive surface, it's away from the conductor. But if the charge is negative, then it's towards the conductor. Direction of field will change. For positive, it's outwards. For negative, it's inwards. Just draw this diagram, and then we'll do next property of conductor. It's simple. If it is positive, then field is outwards. If it is negative, then field is inwards. Okay, let's erase this. I'm erasing it. The next property, fifth property. The fifth, na? First, second, third, fourth. Yes, the fifth property. The fifth property is about electric potential. Electric potential is constant throughout the body of conductor. Throughout the body of conductor. It's constant throughout the body of conductor. It has same value on surface and inside. Exactly same value on the surface and inside. Say this is a conductor. If I say that potential over the surface is V, which is 5 volts, then on each and every point of the surface, your potential is 5 volt. Here too, your potential is 5 volt. Even inside the conductor, your potential is 5 volt. So throughout the body of conductor, your potential is constant. That is the fifth property. So can I say that the surface is equipotential? That's the property of equipotential surface. That potential at every point is same. So you can say that surface of conductor is equipotential. This is the next property. Just note it down, then we'll come to sixth property. Okay. The next property is known as electrostatic shielding. The next is electrostatic shielding. Electrostatic shielding. Here, electrostatic shielding is the phenomena. It is the phenomena of making a region free from any electric field. It is based on the fact that electric field vanish inside the conductor. inside the cavity of conductor. See, electrostatic shielding means, say you have a conductor. Say you have conductor, a solid conductor of some arbitrary shape. And that's a cavity inside the conductor. This is the cavity inside the conductor. It's a cavity. It's a solid conductor. And we make a cavity inside this solid conductor. If I provide some charge to the conductor, then charge will reside only on the outer surface. Charge will reside only on the outer surface. Even if I apply field on this conductor, that field will again resides only on the outer surface. Inside the conductor, charge is 0. Inside the conductor, field is 0. That means this space inside the conductor is shielded from all types of electric fields and electric charge. This property is known as electrostatic shielding. Practically, this property, this electrostatic shielding, can be used to make a space free of electric field. So if you consider a room, even if your room, there are some electric fields, are present in your room. The cause of that electric field, the sources of that electric field is mobile phone radiation. There are wires from which current is flowing. That current will produce electric field. Your mobile phone radiation will produce some electric field. So if you want to make a region of your room free of electric field, then what you can do, you can just take a conductor and place around that region. So if in my room, I want to make this particular region free of electric field. There may be some electric fields in this region due to my mobile phone radiation, due to current flowing through the wire. I want to make this particular region free of electric field. So to make this region free of electric field, I will take a conductor around this thing. I can take a conductor around this region. The net field inside that conductor is 0. So just by placing a conductor around the region, we can make this region free of electric field. Once I place the conductor around it, the net field inside it vanishes. It will be 0. This property is known as electrostatic shielding. So is it clear? Electrostatic shielding, the concept of shielding. Fatma, current flows through a conductor because we apply a constant potential difference. We apply a cell or we connect that conductor to the power supply. It's basically that power supply or that cell which cause current to flow through the conductor. Once you remove that power supply, then current will be 0. So Jubena sir, here cavity is the shield. No, Jubena, here, yes, these walls of conductors are the shield. The region inside the cavity is shielded. So you can say this cavity along with this conductor is acting as a shield. This whole thing is acting as a shield of electric field. So you want to make any region free of electric field, then just place a conductor around that region. The net field would be 0. Fatma asked a very good question, that how does current flow through a conductor then? Because current always flow through a conductor, and current means electric field. Current flows due to electric field. But that current that flows through a conductor is due to cell or battery or your power supply. That power supply forces the electrons to flow in a conductor. Otherwise, if you don't apply a power supply, the net field inside conductor would be 0, your current would be 0. Okay, just answer one more question. So during lightning, is it safe to sit inside a car or outside the car? Say there's thunderstorm and there are chances that lightning could strike on the ground. So what will you prefer, to sit inside the car or outside the car? Outside, okay. Johanna?
Out-
Yes, Johanna, your answer?
outside the car.
Outside the car. Okay, if you stand outside the car, this is the car, this is the body of car. Yes, car is a conductor, right? Car is conducting, car is metallic body. You are sitting inside the car. In case of lightning, lightning means charge, a very heavy charge. In case of lightning, if lightning strike on the body of charge, then due to electrostatic shielding, all of the charge will reside only on the outer surface. This car will act as a shield. It will act as a cavity. The charge will reside only on the outer surface. It will not enter the body of conductor. But so you won't come in direct contact with the charge. Unless you touch the body of the car, you will not be in any direct contact with the charge. So this charge which is flowing due to lightning cannot harm you. But if you are standing on ground alone, then this charge through the lightning will strike you directly. So it's better to be inside the car than outside. Of course,
Sir,
yes.
sir, but then the car, even car has some kind of charges, right?
Yeah, but that charge is on the outer surface only. There's no charge inside. And if
What?
you're sitting on the seat, that seat is insulated from the body. The seat is not metallic, right? That seat is of some non-conducting material. So you are almost insulated with the body of the car.
So what if we are having any gadgets with us?
If you have any gadget which is in contact with the car, because even if you have a gadget in your hand, charge, this charge cannot approach this gadget. It can't penetrate the body of conductor. Even that gadget and you are safe. But if you touch the body of car, then that charge will flow through your body and can harm you. Unless you touch the body of the car, you are safe. Once you touch the body of the car, then that charge will flow through your body and it can harm. Jubena. I'm coming to your question, Afroza. So, Jubena, is it clear? Yeah, Afroza. Now, the question of Afroza is, but it's a very heavy amount of charge. Yeah, there is a limit up to which this conductor will not melt. If the charge is very, very heavy, then yes, it can just melt the whole conductor thing and mess you up. And then it can harm you. But the harm inside the conductor will be less as compared to outside. That's why I'm saying, Afroza, even if your voltage is high, this conductor will shield a part of that voltage. But if that voltage is high enough to melt your conductor, then we can't say anything. But if that voltage is to the limit that conductor can hold it without melting, then it can save you from that charge. But if you're sitting outside, then there's nothing which can save you. Even a small voltage will flow through your body. So during lightning, it's safe inside the car. It's safe inside due to electrostatic shielding. That body of car will act as a shield due to electrostatic shielding. Okay, just note it down. We will erase it. Okay, so I'm erasing it. Huh? Okay, the next thing is spherical conductor. This topic is not given in NCERT, but in NCERT you will find numericals based on this concept. So we won't derive any result, we will see some direct results, spherical conductor. So if you have a spherical conductor, it can be hollow or solid. It's a spherical conductor. Charge will reside only on the outer surface. Charge resides only on the outer surface of this conductor. Charge Q. The radius of the conductor is R. The radius of conductor. Let's consider a point outside the conductor. This point is at a separation R from the center of conductor. We're supposed to calculate electric field over this point. First, we are considering point outside the conductor. We have derived the expression of electric field outside the conductor, and the expression of electric field is 1 over 4 pi epsilon naught. It's Q over R square. This is the expression of electric field outside the conductor. It's 1 over 4 pi epsilon naught Q by R square. This is how we calculate electric field outside the conductor. This we have derived in Gauss law. The potential outside the conductor is 1 over 4 pi epsilon naught. It's Q by small r. And remember, this small r is not the radius of the conductor. That is the separation of point from the center of conductor. We have derived this result in Gauss law, but I will not derive it. This is not given in NCERT. Only in some numericals he is using it. So it's important to do this formula, but I'm not deriving it. If you want to derive it, you can derive it using potential is minus of integral of E dot dr. You can just integrate your electric field. The integration of electric field will give potential. Second, you need surface of the conductor. Surface of conductor. Okay, can you people guess the value of electric field and potential on the surface? What will be the difference in the relation? If I'm taking point on the surface, can you guess the expression of electric field and potential? Yes. There will be a very minute difference. Froza, Fatma, Jubena, Johanna, what would be the difference? No, it won't be E dot ds. I'm just asking about the value of expression of electric field and potential on the surface. What change will be here? When I'm calculating outside, I'm using small r. When I'm calculating on the surface, I will use, instead of small r, what I will use? I will use capital R. Similarly, when we calculate potential on the surface, it comes out to be 1 over 4 pi epsilon naught. It's Q by R. This is on the surface. This is the value of potential on the surface of conductor. Third part, inside. Inside the conductor. Can you guess the value of field inside the conductor?
Is it small r minus big R?
Electric field inside the conductor. Just have mentioned, yes. Electric field inside the conductor is zero. That's the second property or third property. If we are taking a conductor, then electric field inside that conductor is zero. Electric field is zero, but not the potential. We have written that surface, the whole body of conductor is equipotential surface. Means potential is same on the surface as well as inside. So on the surface of conductor, your potential is same. Sorry. Inside the conductor, the value of potential is exactly same as that of surface. That is Q by 4 pi epsilon naught R. Remember this result, we will use this result in many questions. Potential inside the conductor, or you can say that at the center is the same thing. Even at the center, the value of potential is Q by 4 pi epsilon naught R. I'm not deriving that result, you have to remember that potential is same throughout the body. On the surface and inside, the potential have same value. That was property number 5th or 6th, I guess. Just note it down, then we'll do some numericals on this concept. There are few numericals in NCRT on this concept. Completed, okay. Okay. Let's rub it and move on to next question. So you have two conductors. One of radius R1, another of radius R2. The first one, the charge on the first conductor is Q1 and the charge on second conductor is Q2. Let's take 2 points, a point A and a point B. Let's take 2 points, a point A and a point B. So we're supposed to calculate the value of potential on point A as well as point B. Calculate potential at A and B. So you're supposed to calculate potential at point A as well as point B. So potential at point A is, so see both the charges Q1 as well as Q2 will generate potential at point A. So to calculate potential at point A, you have to decide the position of point with respect to charge. I'm solving the first part, potential at A. Potential at A. So potential at A will be due to both the charges, Q1 as well as Q2. So where is Q1? Q1 is on the surface of first sphere. With respect to Q1, point A is on the surface. With respect to Q1, point A is on the surface. Point A is on surface. So with respect to Q1, point A is on the surface. With respect to Q2, see Q2 is on the surface of second sphere. So with respect to Q2, this point A lies inside. Point A is inside. Is it clear, these two statements? Because whole calculation will depend on these two statements. We always see point with respect to charge, that with respect to Q1, your point A is on the surface. With respect to Q2, your point A is inside. So potential at A. So Joanna, what is value of potential at the surface of A? Sorry, at the surface of first sphere? Potential on the surface of first sphere. We just have written the formula. Potential on the surface of first sphere. Anyone? It's an open question for all now. What is the value of potential?
Q by 4 pi
Yes, Q by 4 pi.
epsilon R1.
Yes, Q1 over 4 pi epsilon naught R1. Because potential on the surface is 4 pi epsilon naught capital R, where capital R is the radius. So the radius of the sphere is R1. Now, with respect to Q2, your point A is inside. The value of potential inside the sphere is same as that on the surface. The value of potential inside the sphere is same as that on the surface. So it's Q2 over 4 pi epsilon naught R. Inside is same as that on the surface. So it's Q2 by 4 pi epsilon naught R2. Is it clear? Or I should repeat it? Clear. Johanna, is it clear? Okay. See, you're supposed to calculate potential over this point A. Both charges Q1 and Q2 will generate potential at A. So if you have a sphere having charge Q, the radius of the sphere is R. If I'm taking a point on the surface of the sphere, then on the surface of sphere, value of potential is Q by 4 pi epsilon naught. If I'm taking point inside the sphere, then inside value of potential is same as that of surface. That's Q by 4 pi epsilon naught capital. This is what we have discussed in the last section. Now, over this point A, both Q1 as well as Q2 will generate potential. You just have to decide the position of point A with respect to each of the charges. For Q1, this point A is lying on the surface of charge. Say Q1 is on the surface of inner sphere. A is again on the surface of inner sphere. So you can say with respect to Q1, point A is on the surface. Is it fine, Joanna? Is it clear? The first one. With respect to Q2, where is Q2? Q2 is on the surface of second sphere, right? Your charge Q2 is on the surface of second sphere. So with respect to Q2, your A is inside now. Q2 is on the surface of second sphere. The point A is inside Q2. So potential with respect to Q2, your point A is inside this. Now, the net potential at A is potential due to Q1 as well as Q2. For Q1, point is on the surface. So for surface, it's Q1 by 4 pi epsilon naught R. For Q2, point is inside. Potential inside is same as that on the surface. So it's again Q2 by 4 pi epsilon naught R. Yes, Joanna, is it clear now?
Yes, sir.
Okay. Let's move on to second point. If it is clear, Johanna, then tell me about this potential at B. This is point charge B. So where is B with respect to Q1? Is it inside, outside on surface? Johanna.
Outside.
Yes, it's outside. Good. And what about with respect to Q2?
On the surface.
On the surface. Great. With respect to Q2, point B is on the surface. So potential at B. So outside, the potential is Q1 by 4 pi epsilon naught, the separation between the center of the sphere and the point. So Joanna, what is the separation between the center of first sphere and the point B? Because it's outside, the outside we use Q by 4 pi epsilon naught small r, where small r is the separation between the center of sphere and the point. So what is the separation between the center of first sphere and point B? Joanna?
R2.
What? It's R1, R2?
R2.
R2, right. So 4 pi epsilon naught R2. And what about Q2? What's the potential at B due to Q2? Q2 is on the surface only, yeah? So it's 4 pi epsilon not R. This is potential at B. And this is potential on the surface of first. In the third part, do one more thing. Just subtract VA minus VB and try to prove that this is greater than 0. Note it down and then subtract VA minus VB and try to prove that VA is greater than VB. Try to prove it.
Sir, why is it Q2 by 4 pi epsilon R2 in VB?
Yeah, because
The same.
it is on the surface of the second sphere, right? This radius of second sphere is R2. So potential on the surface is Q by 4 pi epsilon naught capital R. For second sphere, capital R is R2, that's why. Clear? Because this B is on the surface potential is Q by 4 pi epsilon naught capital R, where capital R is the radius of the sphere, which is R2. So shall I erase it? Okay. Now let's check your calculation about VA minus VB. You're supposed to prove that VA minus VB is greater than 0. Third part. So VA minus VB. VB is this Q1 by 4 pi epsilon naught R1 plus Q2 by 4 pi epsilon naught R2 minus of Q1 by 4 pi epsilon naught R2 plus Q2 by 4 pi epsilon naught R2. So this will cancel this term and this VA minus VB is Q1 over 4 pi epsilon naught R1 minus Q1 over 4 pi epsilon naught R2. So VA minus VB is, you can take this Q1 by 4 pi epsilon naught is constant. This is 1 by R1 minus 1 by R. This is VA minus VB, 1 over 4 pi epsilon naught, 1 by R1 minus 1 by R2. Next, you can take this, take LCM here. It's Q1 by 4 pi epsilon naught. You can take R1, R2 as LCM. So this is R2 minus R. Now, since outer sphere, the radius of outer sphere is greater than the radius of inner sphere, so you can say that R2 minus R1 is positive. If it is positive, that means VA minus VB is greater than 0. That means VA is greater than VB. This is an important result. Say this result is independent of Q2. whatever be the charge on the outer sphere, whatever be the amount of charge on the outer sphere, you can put any high value charge on the outer sphere. Inner sphere will always be at higher potential. That's an interesting result. You can see, say, this result depends only on Q1, it's independent of Q2. So whatever be the value of charge on the outer sphere, no matter how high charge is on the outer sphere, the inner sphere will always be at higher potential. Inner sphere is always at higher potential. Higher potential with respect to out. Even this is such an important result that Venn diagram made a generator over this result. This is also known as principle of Venn diagram generator. Although Venn diagram generator is not a part of syllabus now, but earlier it was in syllabus. This is basically principle of Venn diagram generator. So very interesting result that whatever be the amount of charge on the outer sphere, the inner sphere will always be at higher potential. This is known as principle of Venn diagram generator. Just note it down. Yes, this is important. That's a very important question. See, your board is CBSE, and the questions of CBSE are based off NCERT. So each and every line of NCERT is important to you. The board is CBSE, foreign CBSE. So each and every line of NCERT is important for you. If you want to score 95 plus in physics, each and every line is important. So shall I erase it? So that was about electrostatics of conductor. This conductor is very important. You can get direct questions of conductors. Otherwise, you will use conductors in capacitor as well as in current electricity. After conductor, the next is dielectric. This is a theoretical question. If you remember, in the first class of electrostat, you people asked some questions like, what is the physical significance of epsilon naught? I told that epsilon naught is relative permittivity. I told that this is relative permittivity. Someone asked that, what do you mean by permittivity? There's one more very common question, that if I place two charges in air, then the force is F air. What will happen if I place the same charges in medium? Force will remain same or it will decrease? The very generic questions of electrostatics. Like if I take two charges in free space, two charges in air, say you have two charges, a charge Q1 and a charge Q2, placed at a separation R. In air, they repel each other, let's say with a force F air. If I put the same charges at the same separation in some medium, let's say water, what will happen to force? It will remain same or force will change? Yes, force will decrease. Force in water is less than force in air. Force will decrease. The force is maximum in free space, maximum in air. If we keep on changing the medium, the force keep on decreasing. Why force decreases? how a medium affect the force between the two charges. Or the questions like, if you have a charge, you place that charge in free space. Say the value of electric field is E. If I place the same charge in water, Jubana, what will happen to the value of field? I place the charge in air at a distance some r from the charge. I measure field and it comes out to be E air. I took the same charge, I placed this charge in medium, say water, and calculate field at the same separation. Can you guess how this field will change as compared to E air? It will remain
In water, it will increase.
decrease. In water, field decrease. Not just field as well as force. When you place a charge in a medium, some water on any other medium, the force decrease. Now the thing is how medium affect the force between two charges. How medium affect the field of a charge. That is through this topic. The topic we will discuss now. No, it's not about density, of course. It's not about density. It's about polarization. It's about dielectric polarization. Why electric field inside a conductor is zero? We have proved mathematically that electric field inside a conductor is zero, but why it is zero? What happened with a conductor so that field becomes zero? All these theoretical questions will get answered in this topic, dielectric and polarization. So this topic starts with the concept of dielectric. What are dielectrics? Dielectrics are non-conducting medium. Non-conducting, what do you mean by non-conducting? They have free electrons and they don't.
They don't.
They don't. Dielectrics don't have free electrons. But still they transfer electric effect. So material which can transfer electric effect without conduction. So some materials, some non-conducting materials can transfer electric effect but without conduction are known as dielectrics. The examples include like air, water, CO, carbon monoxide. These are examples of dielectrics. These materials don't have free electrons. They can't conduct electricity. They can't conduct charge, but still they can transfer electric effect from one point to another. So these are known as dielectrics. We will see how dielectric can transfer electric effect from one point to another. The next is types of dielectrics. Types of dielectric. We have two types of dielectric. Following two types of dielectric we have is a polar dielectric and a non-polar dielectric. These are two types of dielectric. One polar dielectric, second is non-polar dielectric. We will start this polar and non-polar in the next class. Just note it down. We'll stop here. Okay. So let's stop here. The next class is on today's Tuesday, on Thursday. The next class is on Thursday. So we'll try to finish it up, this dielectric, and we'll start capacitance definitely by Thursday. And can we have an extra class on Friday morning? Can we have?
Okay.
Can you take class at 8 a.m.? as per your schedule, 8 a.m.
Okay, sir.
Okay, let's have a class on Thursday evening. Then I will confirm about the Friday. Friday, maybe we can take a 2-hour class from morning 8 to 10 a.m. So that will boost our sleep. Okay, so let's stop here. We'll continue on Thursday. Joanna, do you want backup of the lectures that you have missed? Or you can do that from the recorded one on the YouTube. Johanna.
I'll check the recorded ones in YouTube.
You can discuss me if you have any doubts on those recording. We can discuss it after the class. When the lecture is over at 8 p.m., we can discuss it after 8 p.m.
Okay, sir.
Okay, Allah Hafiz. Okay, Allah
Thank you.